This is Lecture 2, the Mathematics of Rational Expectations Models. In this lecture, we will demonstrate how to solve a rational expectations model. And as we've learned in years 1 and 2, the economy can be modelled in words, diagrams, and mathematics. And on this course, we are using models that are made up of a system of equations. And these equations represent the agents in the model. So in the most simple form, the supply side will be one equation and the demand side will be another. Remember, the supply side is a set of firms and the demand side is the set of consumers or households in the economy. We will see how these two agents react to an economic shock or economic policy, and in particular we can concentrate on monetary policy. We're going to use some basic algebraic tools and some substitution to help us to solve the model. Last week we discussed the concept of rational expectations and also why we would use expectations in macroeconomic modelling. And this week we're going to present a closed form macroeconomic model with two agents and solve that model using one of three methods A, B and C. Which method we choose will depend on the model type, and that is important that we remember that. Method A is a simple method for simple models, and what we mean by simple models is models in one time period. If there is more than one time period in the model, then we would choose method B or C. That's the method of substitution or the method of undetermined coefficients. We begin with method A, which is the substitution or simple method for a simple model. That's a model where you only see the subscript t and not t plus 1. For t plus 1 we would use a forward variable method. There are two equations, which means there are two agents in the model, one representing the demand side, that's the aggregate demand function, and one representing the supply side. This is the aggregate supply equation. Yt is equal to m bar, that's exogenously set money supply, minus pt, which is the price level, plus some aggregate demand shock, epsilon t. Output supplied is some proportion gamma of the difference between the actual price and the expected price. If prices are higher than we expected them to be, there will be an increase in short-run aggregate supply. And to solve these models, we can take the two right-hand sides and equate them to one another, remembering that the two right-hand sides are both equal to yt here. So we equate the two right-hand sides, and we have equation 3, something we call the reduced form. Gamma pt minus ept is equal to m bar minus pt plus epsilon t. To solve this, we can take expectations of the reduced form, and this will help us to eliminate the unwanted variable, the expectation of pt. We'll be left with a relation then in just pt and m bar, and we have a solution for price. So we take expectations, E of pt is just ept, E of ept is just itself, E of m bar is E of m bar, expectation of pt is E of pt, and the expectation of the shock is E of epsilon t. This simplifies. The left-hand side here is equal to 0, as we can see. One thing minus the same thing is 0. The expectation of m bar is just m bar because it's exogenous, it's a set variable. So the expectation of that variable is just itself. EPT is EPT. and the expectation of the shock is also 0. So we can rearrange this equation to have our first solution for the expected price, EPT is equal to M bar. Now, to obtain the solution for the price level, we can take equation 4 and substitute that into our reduced form equation here. So we take this solution for EPT and use it in the reduced form. And it's the same method every time. Even if you have a different model, you follow the same method. So we can rewrite equation 3 as gamma times PT minus the expectation of PT, which is now M bar, equal to M bar minus PT plus epsilon T. We can rearrange the last equation we gave in the previous slide to give us the solution for price. The PT, equilibrium price, is equal to M bar, exogenous money, plus 1 over 1 plus gamma times the monetary shock. So this is our solution for price. Now to find the solution for output, we can substitute equation 5 into equation 2, which is our aggregate supply curve, to get equilibrium output. So the equilibrium output will be gamma times PT, which will be replaced by this right hand side here, and the expectation minus the expectation of PT. The YT is equal to gamma times PT, which is now replaced with this right hand side, minus M bar. And these two M bars cancel out, so we can simplify the equilibrium YT as equal to gamma over 1 plus gamma times the monetary shock. So that is how to solve a simple rational expectations model. Now we move on to models that have forward variables. So we witness a t plus 1, and if there is a t plus 1 in the model or forward variable, we need more specific methods to solve the model. Here we have the Sargent method of repeated substitution for a forward variable model. And the forward variable model is given. From demand side, we have that output is equal to M bar minus PT, exogenous money minus the price level as before. But now there is this additional term, which we might recognize as expected future inflation. The difference between EPT plus 1 and EPT. That's the shock. This is the aggregate demand relation and the same aggregate supply curve as we gave before. Just as before, we can equate the two right hand sides because they are both equal to exactly YT. And when we do that, we have the reduced form, which is given as gamma PT EPT, that's the aggregate supply, right hand side, and M bar minus PT plus beta of EPT plus 1 minus EPT. So shock is the right hand side of the aggregate demand relation. So there's the reduced form as before, and just as before, we take expectations. Taking expectations, EPT minus EPT equal to E of M bar minus EPT plus beta EPT plus 1 minus EPT plus the expectation of the shock. Do that and rearrange and simplify and have a solution for the expected price level as we did before. This time is equal to 1 over 1 plus beta M bar plus beta over 1 plus beta times expectation of PT plus 1. It's very similar to the previous method, but EPT would be equal to some amount of M bar, but this time we still have the forward variable in the solution for the expected price. Now, in order to try to eliminate that forward variable, that forward expected price, we can rewrite out the solution for EPT, but in the next period, so we can iterate it one period forward. So we do that using the last equation in the previous slide. One period forward is EPT plus 1 over 1 plus beta M bar plus beta over 1 plus beta EPT plus 2. That was t plus 1 before. And we can do that again and again. So we have all these iterations of the same equation. Now to solve this model, we begin by substituting the right-hand side of EPT plus 2 into this term here, or into this relation for EPT plus 1. So we rewrite this out, but replace EPT plus 2 with what is below, the right-hand side of this relation. So EPT plus 1 is equal to 1 over 1 plus beta m bar plus beta over 1 plus beta times EPT plus 2, which is all of this right-hand side. And so we can replace this with all of this, and we do that here. We see that our term is getting longer. And we do that again, only this time we replace EPT plus 3 with the right-hand side here. And we can see that this expression, EPT plus 1, is becoming bigger as we try to substitute out the forward expected price. To begin to solve this solution for EPT plus 1, we can rearrange the terms so that all the m bars are together, and the remainder term, the only one left, which is a forward variable in PT, at the end of that right-hand side. Once we've written it out, previous equation like this, then we could write out one for the nth case. We can see that this is a progression inside these brackets. This is 1 plus beta over 1 plus beta over 1 plus beta squared. So we can imagine the next one will be cubed. We can see that as we iterate further, this is going up in power, and this is going up in terms of j, or future, t plus some future term. This is going up each time. If we iterate it again, it would go to t plus 5. This would be beta over 1 plus beta to the 4. You could write the nth case then as EPT plus 1 times 1 over 1 plus beta times this progression here, which we know is expanding every time we iterate, times m bar, plus there'll be another term at the end, which is beta over 1 plus beta from here, the power n, multiplied by EPT plus n plus 1. We can simplify this further by noting that we can write this geometric progression more simply as a summation. So we write this term as the summation here. So that EPT plus 1 becomes 1 over 1 plus beta from here, then multiplied by the progression, the sum of beta over 1 plus beta to the I, m bar, plus the final term as before, beta over 1 plus beta to the n, EPT plus n plus 1. Now we bring in something, we can see that this is we're never going to get rid of that n term, t plus n plus 1. So in order to do so, we can impose some constraint on the model. We can say that the last term, as n becomes large, you do this enough times, the n term will become 0, so that the limit as n tends to infinity of beta over 1 plus beta to the n, EPT plus n plus 1, will become 0. And we know that this has to be a fraction. Beta over 1 plus beta has to be a fraction, and a fraction to the power of n as n becomes large becomes 0 on its own. So this is intuitive. Now our solution for EPT plus 1 is simpler, as we've lost the second term, which is the EPT plus n term. So our solution for EPT plus 1 becomes equal to 1 over 1 plus beta times the summation of beta over 1 plus beta to the I. This summation, just if we had the sum of a to the I, the solution to this as n becomes large is 1 over 1 plus a, where a here is beta over 1 plus beta. So the summation of beta over 1 plus beta to the I, as n becomes large, is equal to 1 over 1 minus this term, beta over 1 plus beta. And this is just equal to 1 plus beta. Ignore this 1 here. Now replacing our summation with 1 plus beta, our solution for EPT plus 1 just becomes equal to m bar. If this is equal to 1 plus beta, then 1 over 1 plus beta times 1 plus beta is just 1 times m bar. And our solution for EPT plus 1 is here. Now we can use the solution for EPT plus 1 by substituting this into equation 9. To get rid of EPT plus 1, we have our solution for EPT equal to 1 over 1 plus beta m bar plus beta over 1 plus beta EPT plus 1 just becomes beta over 1 plus beta m bar. So we have rewritten our equation 9, our solution for EPT, replacing EPT plus 1 with m bar. And of course this simplifies further. In fact, it simplifies to EPT equal to m bar. So we have the solution now for EPT and EPT plus 1, which we can take to the reduced form to find the solution for PT. And the reduced form with the expectations of prices replaced with m bar is gamma times PT minus m bar equal to m bar minus PT plus beta times m bar minus m bar. This is 0 now. And remember, this was EPT plus 1 minus EPT plus the shock. If we solve for price, we have the solution for price, or equilibrium price, that PT is equal to m bar plus 1 over 1 plus gamma times epsilon t. Now we can use the solution for the expected price and the solution for the price and substitute these two solutions into the aggregate supply equation to solve for output. So our solution for output using the aggregate supply equation, yt is equal to gamma pt minus ept. We replace both these with the solutions. Pt is replaced with this as m bar plus 1 over 1 plus gamma epsilon t, and EPT is replaced with this m bar here too. So this becomes m bar. The m bars cancel out and we have a solution for output that yt is equal to gamma over 1 plus gamma epsilon t. So we've solved a rational expectations model using the substitution method. We now go on to use another method, which is called the Muthian method of undetermined coefficients. So, previous method required us to see the nth solution in the solution for EPT plus 1. It is not required here, so it's different, and it really is a matter of preference whether you use method B or method C for a forward variable model. And we begin with the same reduced form that we had in method B. Gamma PT minus EPT, that's the right hand side of the aggregate supply relation, is equal to the right hand side of the aggregate demand relation. Now we can collect our terms in PT, EPT, and EPT plus 1. We can move all these terms to the left and leave everything else on the right. We have PT, gamma PT minus EPT minus beta, which has come over from the right hand side, EPT plus 1 minus EPT, is equal to m bar minus a shock. So these are the only two terms remaining on the right hand side. And if we write this out in terms of equilibrium price, so we set EPT equal to EPT plus 1 equal to PT equal to P bar. So the equilibrium price is equal to the price, is equal to the expected price and the expected future price. Replace every P term in the previous equation with P bar. We have that P bar is equal to M bar. So we found equilibrium in terms of the constants And now we express that semi-reduced form in terms of the deviations away from equilibrium, or something called prices and shocks only. In other words, we take these constants, p bar and m bar, and remove them from the previous reduced form. So removing m bar and p bar, notice there's no p bar anyway, but removing m bar, we have that pt plus gamma pt ept minus b ept plus 1 minus ept is equal to epsilon t. And we can simplify this by collecting common terms. There's a pt here and a gamma pt, so this becomes 1 plus gamma pt. There is a gamma ept here and a beta ept here. So we have beta minus gamma ept, and so on. So we just leave the shock on the right hand side. For the Muthian method, we need to propose a general solution just as we do when we're solving differential equations. A general solution that has undetermined coefficients, here pi 0 and pi I. We find the value of these coefficients, and that gives us the solution, the price. We start with the proposed solution. Pt is equal to p bar, the equilibrium price, plus pi 0 epsilon t, and the stream of coefficients pi I, which are attached to the shocks in the past, t minus I. As I goes forward, the shocks go further in the past. And we can rewrite this, as we're only interested in deviations from the steady state, without p bar. So we've written the same equation without p bar. We then take the expectation of this equation to get a solution for ept, and then we take the expectation of this equation, pt, in a forward period to also get ept plus 1. And we'll do that now. So first of all, we take expectations of the equation above. ept is equal to the summation of pi I epsilon t minus I. And notice that we've lost this term because the expectation of the shock is 0, but we have not lost this term because these are past shocks, so they're already realized. So there is our solution for ept. We roll this previous solution one period forward here. We just add 1 to all the t subscripts, and then we take the expectation of this to get our solution for ept plus 1. Again, we lose the first term and also the current term, and we have that ept plus 1 is just the stream of undetermined coefficients pi I times epsilon t minus I plus 1, and we can rewrite that here slightly differently by rolling back the I subscript. We take equation 14, which is the reduced form in terms of shocks and prices. We can homogenize it. So bring all the variables from 14 over to the left hand side, and that means on the right hand side we just have equal to 0. We then replace pt, ept, and ept plus 1 with their solutions that we found in the previous slide. So pt is replaced with this solution for pt, ept is replaced with this solution for ept, and ept plus 1 is replaced with the solution for ept plus 1. We now know that this holds in every period, so we can take each period, so we can collect the undetermined coefficients, and for epsilon t, this is going to be equal to 1 minus 1 plus gamma pi 0. Now no other epsilon t's here, so it's equal to 0. And we can rearrange this so we know I have a solution for pi 0. That's the first coefficient. Pi 0 is equal to 1 over 1 plus gamma. For the past shocks, we have coefficients minus 1 plus gamma times pi I, minus beta minus gamma times pi I, and beta times pi I plus 1. we've written here, equal to 0. The coefficients must be equal to 0. We divide through by pi t minus I for that particular period. Rearranging this, we have minus 1 plus beta pi I plus beta times pi I plus 1 equal to 0. We can bring pi I onto the right hand side and we have a solution, semi-solution pi I plus 1 equal to 1 plus beta over beta pi I. This is a difference equation, and that difference equation in pi I has the following solution. Pi I is equal to 1 plus beta divided by beta to the I times pi 1, like a starting value, the first value of pi. Since 1 plus beta over beta is greater than 1, in order to get solution stability, because this will just grow with every increase in the powers I, we need pi 1 to be equal to 0 to get a stable solution. That's the only solution we can have without an explosive path for pi I. Therefore, the only stable solution is pi I equal to 0. In other words, the agents know that the other solutions are irrational, and so they rule them out. They know that the only solution is that pi I will be equal to 0 in the future as I progresses. Now we can, with the values pi I is equal to 0 and pi 0 is equal to 1 over 1 plus gamma, we can put those back into our proposed general solution to get the solution for the price level. So remember, our proposed solution was P equal to P bar plus pi 0 epsilon t plus this stream of coefficients attached to the shocks in the past, giving pi I equal to 0 means that this solution for Pt reduces down to Pt equal to P bar plus pi 0 epsilon t. And we know that P bar is equal to M bar, and we know that pi 0 is equal to 1 over 1 plus gamma, so we can just replace those, and we have a solution for price. If we take expectations of that solution for price, we know that EPT is equal to M bar. We can then use the solution for price and the solution for the expected price, substituting into the aggregate supply relation just as we did before in the previous method. The YT is equal to gamma times PT, and this is the solution for price, minus EPT, which is now replaced with M bar. And this reduces down to just equal to gamma over 1 plus gamma epsilon t. And compare the results from methods B and method C, and you will see that they are equivalent for the same model. So there is a choice between method B and C when you are applying them to a forward variable rational expectations model.